Welcome to the CFE Media and Technology Education Session, How to Design Healthcare Power Systems. I'm your moderator, Amara Rozgis with CFE Media and Technology. In keeping with our CEP policy, please take some time to read the quality assurance slide. This session is designed for technicians and engineers who want to understand the fundamentals of designing healthcare power systems. Here's a list of learning objectives. We'll touch on these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes within this session, click on the left panel labeled Notes to do so. The session is available on demand if you need to come back at any time. Please remember that this session is made live at 10 a.m. Central, 11 a.m. Eastern. The Q&A starts at approximately 10:45 Central or 11:45 Eastern, or immediately after the presentation ends if we run a little long. Two industry experts will answer viewer questions live, and those answers will be archived with the session. And you can see those Q&A details in the Meetings tab on the left side of the screen. Here's some information about obtaining approved PDHs for today's session. Before tuning into our presentation, we'd like to share a brief video from today's sponsor.
The world is facing an ever-growing demand for power. So we're looking beyond today's challenges with the drive to invent power solutions for the new world you work in. With digital-driven engineering and thinking that have reinvented power generation to meet critical needs. With the vision to create entirely new power technologies for you, for the world, and for the future. And the imagination to rethink the concepts of sustainability and true energy independence. The people of Cummins have our eyes on your future and are the driving force behind the next generation of power.
Today's speakers are Jeff Yates and Chad Hale, both with Cummins. I'm your moderator, Amara Rozgis with CFE Media and Technology. All right, well, Jeff Yates has been with Cummins for 3 years within the Application Engineering Group. Jeff has 25 years of electrical engineering experience covering multiple facets of electrical infrastructure, including power generation, low voltage electrical distribution, and various applications. Chad Hale is a technical marketing specialist with Cummins. He has a background in global supply chain management, technical development, and sales. He supports the upstream influencing initiatives through the technical marketing team. Chad is a recent graduate of Purdue University and has been with Cummins since June 2019. Please enjoy this tutorial, note any questions you have along the way, and then join Jeff, Chad, and me for the question and answer session. You can see the Q&A details in the Meetings tab on the left side of the screen. All right, Chad, let's get started.
All right, thank you, Amara. I appreciate the introduction, not only to this event, but to me and Jeff as well. So before we get things started, I'd just like to go ahead and read a quick disclaimer for you all. The views and opinions expressed in this course shall not be considered the official position of any regulatory organization and shall not be considered to be nor relied upon as a formal interpretation. Participants are encouraged to refer to the entire text of all reference documents. In addition, when in doubt, reach out to the authority having jurisdiction, otherwise known as your AHJ. All right, so to kick things off, for the codes and standards portion of the presentation, I want to start with what I'm sure most of you are aware of, and probably one of the most well-known codes and standards associated with healthcare systems, and that is, of course, NFPA, or the National Fire Protection Agency. So what does NFPA mean for a healthcare application, you might ask? Well, to start off, NFPA lays out the requirements that cover the performance of an emergency and standby power systems, providing alternate ethical power to the loads in a building and facilities in the event that a power source fails. NFPA also lays out the requirements as it pertains to an emergency power supply system, as well as maintenance and testing requirements, which we will discuss in the back half of the presentation. As always, the intent of NFPA and its underlying codes are to achieve the maximum system reliability for an emergency power supply system. Now, quick note for those tuning in from Canada or associated with Canada, I will discuss CSA 282, which is a parallel to NFPA. But one common requirement for healthcare systems is that an emergency power supply system with NFPA be a NFPA 110 Type 10 system. So once again, you may be asking yourself, what does this mean? This is a lot of words, a lot of numbers. Well, for starters, NFPA defines a type as the maximum time in seconds that the emergency power supply system will permit the load side of the terminals of the transfer switch to be without acceptable power. Now, this can be found in reference in NFPA 4.3. And it is the time the generator has to operate after a power of failure. So that means that a Type 10 emergency power supply system must be able to provide acceptable power to the load side of the transfer switch within 10 seconds of an outage. That also, keep this in mind, includes all intentional and unintentional delays associated with the transfer. As it pertains to Canada and CSA, there are similar requirements for emergency power supply systems, and that would be within CSA Z32, and within Z32, if you look at Chapter 6.2, you can find similar requirements as it pertains to the starting capabilities of an emergency power supply system within a healthcare facility. So as for a deeper look into NFPA 110 and all related content, please click on that link and it will take you to more details. So next on the list of codes and standards associated with emergency power supply systems is NFPA 99. NFPA has a multitude of codes that outline the requirements for a multitude of applications and equipment. However, specifically for healthcare, we need to look at and take a look into NFPA 99 as it pertains to healthcare facilities and the code. Within this code, there is a wide range of topics covered. However, for emergency power supply systems, you will want to take a deeper look into Chapter 6. Within Chapter 6, NFPA provides guidelines very similar, but not an exact copy of NFPA 110, that lay out the requirements as it pertains to the performance of an emergency power supply system. Now, what does this all mean for you as a facility manager or someone taking over and looking at emergency power supply system within a healthcare facility? That is the installation, maintenance, and operational testing guidelines, all with the intent, just like NFPA 110, to achieve maximum system reliability for your EPSS. The one thing to note within NFPA 99 that is a distinct difference from NFPA 110 is that NFPA 99 divides the essential electrical system into three branches. You have life safety, you have critical, and you have equipment. So be on the lookout for that being called out within the code and as it relates to you and your emergency power supply system. Next up on the list is NEC 700.3. If you have an emergency system that relies on a single alternate source, this could be a single generator. What this means is that you have an emergency load that is powered by a single generator, and if it goes down for maintenance or repair, then as a design principle, you need to have a permanent connection for your portable or temporary generator built into the system design. NEC also goes on to say that this temporary source needs to be available for the duration of this repair or maintenance. So with that being said, if your emergency power supply system meets those requirements of needing a temporary source of power, then you need to make sure that your temporary source of power should comply with the following. The following being that shall not require modification to the permanent system wiring, transfer of power between the normal power source and the emergency power supply source shall be in accordance with NEC 700.12 or 12. The connection point for the portable or temporary alternate source shall be marked with the phase rotation and system bonding requirements. NEC is just trying to remove any chance of human error, and by marking your connection points, this should help eliminate any of those issues. Mechanical or electrical interlocking shall prevent inadvertent interconnection of power sources. Once again, NEC is just going back to the safety aspect of things, so that if the emergency power supply system is under repair, then the temporary source does not supply power back to the permanent generator. So the interlocking prevents this from happening, keeping everybody safe down the line. The switching shall include a contact point which shall enunciate at a location remote from the generator or at another facility monitoring system to indicate that the permanent emergency source is disconnected from the emergency system. This is just allowing the operator to know when the permanent generator is disconnected from the system, and ideally a temporary generator has been connected. Now, with this diagram, we can see a locking system in practice. By looking at the diagram and by thinking about this from the transfer switch perspective, this is a great example of how a transfer switch does not know whether the temporary source is connected or the permanent emergency source is connected. So if the utility does fail, as long as the start signal comes through, it will start the generator for whichever side it is flipped to during maintenance, allowing for no reconfiguration, which is once again one of NEC's big requirements, so that the system and the operator shall not be required to modify the wiring during a service event. So we've talked about NEC, we've talked about NFPA 99 and 110. So outside of NFPA, there are many other local national codes that can affect a healthcare installation. A perfect example being the Joint Commission and their Environment of Care Standard. What does this mean for a healthcare installation? For starters, it reinforces the NFPA testing and maintenance standards, which I will discuss later on in the presentation, and that is that an emergency power supply system must be tested 12 times a year at intervals no less than 20 days and no more than 40 days. When testing an emergency generator, it must be for at least 30 continuous minutes, and the test dates must be documented. The emergency generator tests are conducted with a dynamic load that is at least 30% of the nameplate rating of the generator or meets the manufacturer's recommended prime movers, EGT, or exhaust gas temperatures. As always, it is recommended that you are consulting your AHJ or authority having jurisdiction, as they might have requirements that go above and beyond that of NFPA and other codes and standards. Before we move on to testing and maintenance, I will discuss quickly CSA, as I mentioned it before. So with emergency power supply systems and its association with CSA, that there's the two major things to consider when looking into a healthcare application in Canada, and that is CSA 282.19 that deals with emergency electrical supply for buildings, and lastly CSA Z32 or Z32 if you are Canadian, which deals with the safety and essential electrical systems as it pertains to healthcare facilities. So just keep those in mind if you're looking at applications north of the US. So I mentioned we talk about testing, and here we go. In healthcare applications, the reliability of an emergency power supply system is top priority. And one way to ensure the reliability is through proper testing and exercising of your emergency power supply system. NFPA outlines in section 8.4.2 how to test an emergency power supply system monthly. To start off, these monthly tests must be a minimum of 30 minutes using one of the following methods. Method one being loading that maintains a minimum exhaust gas temperature as recommended by the manufacturer. And the second one being, the second point states, under operating temperature conditions and at no less than 30% of the emergency power supply system standby kilowatt rating. As a note, make sure to always be double checking with your AHJ, as some areas may have more stringent requirements as to what kilowatt rating needs to be met and maintained during this 30-minute testing window. So outside of the monthly testing, there are 36-month testing. So the next step in the testing process for a healthcare facility is 36-month testing. So when testing at the 36-month mark, what should a facility manager be looking into doing as defined by NFPA? So for starters, the emergency power supply system needs to be tested for a specific duration as defined by the class. Now you may be asking yourself, what is a class? A class, as defined by NFPA, is the minimum time in hours for which the emergency power supply system is designed to operate at its rated load without being refueled or recharged. And that it can be found within NFPA 4.2. Next up, if the emergency power supply system is assigned to a class greater than 4, then it shall be permitted to terminate the test after 4 continuous hours. The minimum load for 36-month testing can be found in sections 8.5, 9.1, or 0.2 or 3. Lastly, these 36-month tests can be combined with those monthly tests that I just talked about previously, as required in section 8.4.2, and one annual test as required by 8.4.2.3. But keep in mind that is only as a single test. And then lastly, in addition to all of this, it is recommended that a permanent load bank be specified to allow for proper loading during the weekly testing. So we've talked about testing, we've talked about codes, and now it's time to talk a little bit about maintenance. So when looking into how to best maintain an emergency power supply system, there is no better place to look than NFPA, more specifically Chapter 8 of NFPA 110, which is what we're looking at right here on the screen. The first thing called out within Chapter 8 is the need to base maintenance and operational testing off of the manufacturer's recommendations and the need to reference instructional manuals. Now, this is no coincidence. You may be asking yourself why the manufacturer, and that is because as manufacturers tend to know best as to how to maintain any piece of equipment to keep it in tip-top shape in the best working condition possible. So it is important for facility managers to reference those service manuals and utilize local technicians to ensure that their emergency power supply system is being properly maintained and tested at the right intervals for their EPSS. Next, NFPA has also done a great job of working in alignment with the manufacturers on these emergency power supply systems to lay out the basic minimum requirements as it pertains to the testing and maintenance of an emergency power supply system. If you need more information for those basic requirements, please make sure to read through Chapter 8 of NFPA 110. The last point within Section 1.1 of Chapter 8 is in reference to your local authorities having jurisdiction, or once again, your AHJs. These AHJs are called out due to the simple fact that NFPA 110 is not an all-encompassing standard, and outside of NFPA, there are various other local and national codes as it pertains to healthcare. One of those is the Joint Commission, as well as NFPA 99, that are both examples of requirements that are both in line with NFPA, but also build upon the code as well. Another example would be if a healthcare facility were to have a Tier 4 certified product to meet the needs of EPA stationary non-emergency regulations. There exist maintenance requirements for the after treatment on those products that must be maintained. This may include key maintenance points of the diesel particulate filter, or the DPF, and components around the storage and delivery of DEF, or diesel exhaust fluid, in the system. So for example, it is important for facility managers to understand that local and specific codes may have requirements for an emergency power supply system that goes in above and beyond that of NFPA 110. there's some more information if needed. So for fuel quality testing, that is another big thing for emergency power supply systems. Fuel quality testing is another common key component to the reliability of your emergency power supply system. This is due to the fact that much like any other things in life, fuel degrades over time. And it is with this degradation that you can have issues that can affect the emergency power supply system's ability to operate at 100%. So facility owners need to inspect and take action in order to stay ahead of these issues. NFPA outlines how to best do this in section 8.3.7, which states a fuel quality test shall be performed at least annually using appropriate ASTM standards or the manufacturer's recommendations. Now, Cummins recommends that fuel be tested at least once a year, and depending on the size of the installation, you may want to test more regularly, and the same is said for installations where there is a known fuel quality issue. Many manufacturers have the ability to provide fuel testing through these agreements. Another key tip to getting a great baseline test is getting a proper baseline test with diesel fuel sample as a result of the fuel as it is delivered in the tank during the commissioning phase of the generator set, and will be most helpful for the facility owner down the line. So one of the last things I'll talk about is compliance reporting. As we all know, generator serves as reliable emergency backup power in a multitude of critical applications, including healthcare, but not limited to healthcare. And because that reliability is so important, NFPA requires an established record of maintenance and operational testing for those emergency power supply systems. Several other compliance agencies refer to these NFPA guidelines as well as it pertains to compliance reporting. Examples of those being your Joint Commission, your local AHJ, Centers for Medicare and Medicaid. So it is important to look into those as well when trying to figure out what is best for your emergency power supply system and compliance reporting. So as a facility manager, what should you be looking for in a platform as it pertains to compliance reporting? For starters, you would want to look for the ability for one-click reporting and the advantages that one-click reporting provides. For instance, the ability to have pre-formatted and pre-approved NFPA 110 templates, the ability to make a pass-fail assessment, and lastly, to provide a single report per site. The ability to leverage the start stops of the generator is also a big advantage of remote monitoring as it pertains to compliance reporting. And I have an example of what one of these test screens might look like, or one of these compliance remote monitoring systems looks like. So here's an example of what a solid test report would look like and what to look for in remote monitoring. So here you can see you have your data summarizing the test results. You have the graph and then a pass-fail up there. So this is the summary table with editable fields for test results. So you can have your drop-down with pass-fail up there. You can see this test was a pass. And then it goes to a different tab. So this is a great example of what you would be looking for when it comes to results. So you can have your reports up here. You got a lot of options. You got your test date and time, what type of test it was, your test summary, test duration, all that good stuff. So this is all what you should be looking for in a remote monitoring service. And then off to the right here, you see your ability to create a report, discard test, and then once again, you have that test duration there. That is all logged for you on this remote monitoring service. And then another great feature to look for in a system is to have the ability to go back and look at past recorded tests. So whether that be the test that you did today or the test you did, as you can see here, you have the ability to go back and look 45 days in the past. So those are all great things to look for in remote monitoring services. Next, I will hand it over to Jeff to walk us through some case studies. So, all right, Jeff, here you go.
Great, thank you, Chad. Excellent job. So what we'd like to do is just kind of bring some of this application that Chad references to reality, and just share a few of the case studies that we have chosen that have a little bit of a unique factor to them. We'll find that we think it would be very interesting. So first of all, our first case study is Our Lady of the Lake Medical Center in Baton Rouge, Louisiana. Within the hospital, we have one 1750 kilowatt diesel application. We have 5 1750 kW lean burn natural gas units. We have some digital controls. We have paralleling switchgear, transfer switches. And the application is emergency standby along with supplemental power. And I'll explain what that means. But Our Lady of the Lake is a hospital in the Gulf States region of the US. As you know, this region of our country is susceptible to hurricane and tropical storms. In fact, the Gulf has had another active year in 21, most recently Hurricane Ida. One significant event changing our approach to hurricane preparedness was Hurricane Katrina in 2005. It was devastating, causing 1,800 deaths, 125 billion in property damage. Katrina activated new measures in storm readiness, including changes in overall preparedness to supplies and transport. For us in the power generation, this meant looking at alternative measures in fuel supply and how to minimize its impact to flooded regions. Natural gas could be a solution. Feasibility studies pursued as Our Lady of the Lake considered this alternative fuel in future power plant renovations. Our Lady of the Lake is a major hospital in the region. They have 763 licensed beds, and they were adamant in reducing their risks to subsequent storms in the future. NFPA 110 Type 10 still applies here, as electrical power within life safety must be restored to power side of the ATS within 10 seconds. Therefore, the hospital planned one 1750 diesel to cover this Type 10 requirement, Article 700, as well as 701, and added 5 additional natural gas 1750 kW units to cover the remaining power needs of the hospital. So how did this all work? At power failure to normal side of the hospital, all 6 of the generators receive a signal to start and close to the common bus. Diesel will, of course, close first and supply the power to the life safety loads. The remaining 5 gensets will sync to a live bus and supply power to the remaining hospital power grid connected to the emergency standby. Upon synchronizing to the live bus, the natural gas units will assume load of the life safety, and the diesel will drop off the live bus and start its cool down proceedings, and then return back to standby readiness. So why is the natural gas an advantage? First, it's an unlimited supply of fuel the hospital can use until normal power is stable and returned to the grid. During catastrophic events, this could be weeks, as you know. Secondly, it's a cleaner burn, a more environmental friendly to carbon emissions. Third, there are additional cost advantages in implementing natural gas units, as the hospital can now take advantage of peak shaving exercises with local utility. This was part of the hospital's initial plan to have the option of peak shaving in the future and to have the infrastructure in place to execute if desired. Therefore, at peak times when the kW prices are high, the hospital could exercise their natural gas units in providing power to their facility in lieu of paying utility for power. Our second case study is Oregon State Hospital in Salem, Oregon. With this application, we have two meg units, 2000 kW diesel, with specific enclosures with a low dBA. So they have 65 dBA sound attenuated enclosures, which brought its own challenges. Parallel switchgear. They also have a DMC, a master controller, 14 sections of switchgear, 9 bypasses, switches on campus. So the application was, of course, emergency standby system, the power source for local utility, which in this case is Portland General Electric, which we will refer to as PGE. So the overall purpose, Oregon State, it's unique in that it had 4 utility feeds supplying power to different locations on campus. So the goal was to consolidate this power plant into one primary utility with one distribution system, as well as provide one standby power generation system coordinating with new utility. Other challenges include sound attenuation to 65 dBA I mentioned earlier. It was in tight quarters where gensets will be installed, including the digital controls. There were tight deliverable schedules at the time, so there were many extracurricular challenges that we had to contend. Oregon State partnered with Portland General Electric, PGE, as I referenced, giving multiple advantages besides normal power to their facilities. PGE has a program titled Dispatchable Standby Generation, where PGE will front a portion of the initial costs and operational costs to standby power applications. PGE will cover routine maintenance and fuel costs for use of standby emergency system. PGE will also front costs for additional paralleling switchgear, allowing the gensets to be monitored and operated by PGE. So what does this mean? Oregon State Hospital will have emergency power to supply their facility to the normal power failure. Costs of maintaining and fuel will be paid by PGE. In turn, PGE will have an option to access Oregon State's gensets in high demand periods throughout the year to backfeed power to the grid. This gives PGE stability to the grid and lessens the need to find other alternative power sources, for example, renewables. To accomplish this, Oregon State Hospital has 2 switchgear lineups, one for the hospital, one for the grid. The hospital can apply their standby procedures in normal blackout situations. PGE can also monitor and call for the standby generators to the grid in critical times needed. So it creates a win-win scenario for both. Finally, in our third case study, we'll talk about a Canadian application, Alberta Children's Hospital, located in Calgary, Alberta, Canada. It has 3 2,000 kW medium voltage application. Also has paralleling gear, digital controls, has a remote power generator generation facility, so it's not actually included in at the hospital campus. And there are a number of step-down transformers supplying the 347 600 volt from the medium voltage application, and I'll explain in a minute what that means. But the idea is to provide standby and utility outage. So Alberta Children's Hospital is a new build specifically built for children from a unique building facade, imitating colorful building blocks, exterior to the interior, promoting healing. 133 licensed bed, 750,000 square foot facility, supported by 3.5 megawatt of electrical power. One attribute to this facility at the time of build was constructing a separate remote facility to house their standby power generation. The remote location improved functionality as well as performance to the hospital. A separate building allowed better airflow for cooling, reduced noise pollution as gensets were enclosed in separate quarters from the main campus. Vibration was also not a concern on the adjacent floors, as it didn't apply. Remote location also improved maintenance and service schedules, as access was easier in lieu of negotiating above grade or below grade floors in normal hospital applications. Remote does mean remote in terms of distance. The power plant was 400 meters from the main campus. That's 1,312 feet for us. To accommodate this distance, medium voltage was applied. 4160 volts was applied from the power plant to the hospital penthouse, then stepped down to the 340 600 volt, as mentioned earlier. All the testing performance exceeded the expectations of CSA's Z3204 standard, were met at the 10-second intervals in lieu of the standard's requirement of 12, which is different for the Canadian standards. Fuel capacity for this project was 50,000 liters, equivalent to 44 hours of runtime. So to recap the applications that we've shared, we had 3 unique standby applications serving healthcare needs and their requirements. Related to Lake, applied 2 fuel sources, diesel and natural gas. Diesel met the type 10 expectation. Natural gas gave the hospital longevity and power supply with the unlimited fuel. This project also brought cost advantages of natural gas and alternative to peak shaving practices. Oregon State applied 2 parallel gensets as well as paralleling with the local utility. By accessing the local utility, saved the hospital dollars spent on fuel and maintenance, as well as some upfront costs in infrastructure, paralleling switchgear. In turn of costs passed to utility, it gave the utility access to their power plant for critical power needs and high demand use. And finally, we shared Alberta Children's Hospital applying a separate facility designed for their 3 2-meg units, supplying the hospital at a medium voltage 4160, then stepping down the voltage at the hospital's main campus. This remote facility improved overall performance for the hospital in means of sound and vibration reduction, improved cooling, serviceability to the power supply system. So we hope you found some of this information useful with these applications. And with the Cummins engineering teams, we both corporate and remote, we'd be happy to provide any assistance in any of these applications as questions may arise. So Chad, that's all I have. So if I may, I'll pass it back to you.
Yeah, perfect. Thank you, Jeff, for those wonderful case studies. So as we wrap up the presentation, we just kind of want to remind and thank everybody for attending this presentation. We hope that you were able to learn some stuff about NFPA 110 as it pertains to your class and your section, and what it means to be a Type 10 system, as well as what it means to be a healthcare facility manager with the other codes of standards, so NFPA 99 and NEC. As well as learning the best way to maintain your generator set, whether that be through testing or maintenance or fuel testing, stuff like that. We hope that we were able to educate you and answer any questions that you may have and work through some questions via case studies. So with that, I will now hand it back over to Amara.
Excellent. Thank you so much, gentlemen. Thank you, Chad. Lots of good information. And Jeff, those examples were great. And now it's time for the Q&A portion. Please submit your questions using the Zoom question and answer interface. Today's presenters are Jeff Yates and Chad Hale with Cummins Power Generation. I'm your moderator, Amara Rozgis with CFE Media and Technology.